Hi everyone. This is a lesson on linearization and the linear approximation. So we're going to start by understanding the words local linearity. And what this means is that if f of x, cross out this, if f of x is differentiable at x equals a, if f of x is differentiable at x equals a, then when we zoom into that point at x equals a, f of x will look more and more like a straight line, okay? This does not happen if f of x is not differentiable at x equals a. So let me just explain that a little more. So if I have a function and we have some point x equals a, and this function is smooth, right? So remember, differentiable means smooth. So here I am at x equals a, function looks very smooth. If I keep zooming in further and further to that point, I mean, I'm doing it right here, you can see that stretch of the function looks more and more like a line. So that's really what local linearity means. If you zoomed into a function that's not differentiable, for example, if we had a function that at some point a looked like a sharp corner, for example, if it had a sharp corner like that, right, we know that means the function is not differentiable. Well, if I zoom into this, right, no matter how much I zoom in, I see like a little notch. It doesn't look like a line. So that means that function is not locally linear, right? This function is locally means around x equals a, right around x equals a, we look like a line, we're linear, right? This one here is not locally linear at x equals a. So this is our idea that we're working with today. So because of this property, if f of x is differentiable at x equals a, then we can use the tangent line at that point as an approximation for the actual graph, right? So let me go back to my picture here and say I can come to that point x equals a, and you can draw a little tangent line right there, right? We've spent half this year, basically all the months till now, learning about this tangent line, right? So this tangent line and the function look very much like each other right near the point x equals a. That only happens if the function is differentiable there. And if it is, we can use that red line as an approximation for the blue line. That's really what our lesson is about. So let's just learn the theory here. If we have this point A, right, then the y value is f of a. So we have a point. At that particular point, I can find the derivative of the function and evaluate it at that point, right? Then I would have the slope at that particular point A. So I can simply write my point slope equation. Remember, this is like my x1, y1, and this is my m. So I can write y minus y1 is equal to m times x minus x1, right? We've been saying that all semester. But now we're just going to replace y1 with f of a, because that's where we are, and x1 with a, because that's where we are. So I can write this green equation like this using f of a and a for y1 and x1, and using f prime of a for the slope. So y minus f of a equals f prime of a times x minus a, that's this equation. And then if I add f of a to both sides, I get that y is equal to f of a plus f prime of a times x minus a. So this is the equation of the tangent line at x equals a. And since we're saying that this line is very important in that it looks almost like the function, so long as you don't go far away from a, we're going to give this line a name, which is called L of x, and this is the linear approximation for the function at x is equal to a. So this is our linear approximation equation. L of x is equal to f of a plus f prime of a times x minus a. This is called the linear approximation or the linearization. And it basically, as I explained, means that we're using the tangent line as an approximation for the graph of f of x, or the curve of f of x. Okay, so let's go ahead now and do example 1. So in example 1, the first part says find the linearization of f of x equals rad x at x equals 9, right? So we're working with the function f of x is equal to rad x. This is a function that's quite familiar to us, so we know that it looks like the 1 goes to 1, and 4, the square root of 4 is 2, and then the square root of 5, 6, 7, 8, 9, the square root of 9 is 3, and we know this function has this kind of a shape. That's my rad x curve, right? So what we're saying is we're going to this point at 9 and trying to write the linearization, or the linear approximation, which basically means the equation of that tangent line, right? So we have a formula that we just developed. L of x, which is the equation for that line, is going to be equal to, I'll just write the formula first, f of a plus f prime of a times x minus a, okay? Now, every linearization problem will give you a specific x value. That specific x value is our a for this problem, right? So for this problem, a is equal to 9. Okay, and we put that a back into the function to get f of a. So f of 9 is equal to square root of 9, which is equal to 3. So I have both a and f of a. That's the x and y values of the point where I'm making the linear approximation. So the only other thing we're going to need for that equation, L of x equation, is to find the slope, right? So we need f prime of 9. So we know that f prime of x is equal to 1 over 2 rad x. We've done this many times. That's just the derivative. I can put in 9 and get out that f prime of 9 is equal to 1 over 2 times 3, or 6, right? The square root of 9, remember, is just the positive square root, or 3. So I have everything I need to go back in here and write the equation of my linear approximation. L of x is equal to 3 plus 1/6 x minus 9, right? So that's simply plugging in the values into that. And I now have the equation of this red line, the tangent line, at that particular point. Okay, and then the next part says use a linearization, which we just did, to estimate the square root of 9.2 using a linear approximation. So let me just try to explain what that question means. We're saying that, we're on this black curve, the square root of x curve, right? And we know that, if I put in 9.2 into the square root of x, I'd get some decimal number on this black curve, right? Now, we could get an exact number going in a calculator, but we can use this linear approximation to get a very close approximation of that exact answer, right? Because at that point, right around 9, this red tangent line and this black curve are almost indistinguishable. I mean, they're very close, right? They're not exactly the same, but they're very close. So if I wanted to calculate f of 9.2, right? That's, if I wanted to do square root of 9.2, that would be f of 9.2. I'd have to go into a calculator to get that exact value, and I can do that. But I can also make an approximation for this by finding L of 9.2. And that's what we're going to do for part B. We're just going to use this equation in here and put in 9.2 for x. So L of 9.2 is 3 plus 1/6 9.2 minus 9, which is 3 plus 0.2 divided by 6. And this answer is 3.0333. Recurring, we're going to just cut it off at 4 decimal places like we always should for our AP format. So that's the linear approximation of the square root of 9.2, right? So square root of 9.2 we're saying is approximately equal to that. If you went in your calculator and you did the square root of 9.2, right, you would get a number that's very close. So if let me just write it here. If I go in my calculator, I get the square root of 9.2 is equal to 3.033150178, right? So we can see that the linear approximation which used this line equation to get that answer was very close to the actual answer. And in more advanced calculus classes, we talk a lot about the error between the linear approximation and the exact answer. But the important point to note is that linear approximation can be very useful. This was a very simple function. If you had a more complicated function, as you often do in engineering and science, you can, instead of making an exact answer, we can make a linear approximation and make the problem much simpler while still getting a lot of accuracy. Okay, let's do another example. So example 2, if f of x is equal to rad x plus 3, find an equation for the tangent line to the graph at the point where x equals 1, right? So this, by the way, means exactly the same as find the linearization or the linear approximation for f of x at x equals 1. So for part A, our point where we are is 1, and the y value there is the square root of 1 plus 3, which would be the square root of 4 or 2. And now we are just using the linear approximation formula, so we need f prime of A, so f prime of 1 is 1, so I should really say f of 1 is 2, and f prime of x is, by the chain rule, 1 over 2 rad x plus 3, and then the inside derivative is just 1, so really it's 1 over 2 rad x plus 3. So f prime of 1 is equal to 1 over 2 rad 1 plus 3, which is equal to 1 over 2 rad 4, or 1 over 4. So my linear approximation L of x, which is the equation of the tangent line, just written in a different format, is f of a, that's 2, plus f prime of a, that's 1/4, times x minus a, which is, in this case, the a is equal to 1, right? So let me just remind you again, the formula we're using is f of a plus f prime of a times x minus a, right? So I've just put in this particular problem, a is 1, f of a is 2, and f prime of a is 1/4. So just put in those numbers here to write my tangent line equation, okay? That's part A. Part B says use this linearization, this tangent line equation, to approximate f of 1.05. So all we have to do is put in 1.05 into the line equation and get 2 plus 1/4, 1.05 minus 1, which will be 2 plus 0.05 divided by 4, and that comes out to be, let's see, 2.013. 2.013, actually, let me get it to one more decimal place. Let me make sure. 2 plus 0.05 divided by 4 is equal to 2.0125. I like it better that way because we are consistent with 4 decimal places. So that's the linear approximation. If we did the actual f of, let me just do that up here, f of 1.05, right? If I put that in for x here, I get the square root of 1.05 plus 3, and that is actually equal to 2.01246, 1180, right? So notice, very, very close. The linear approximation is getting us very close. Okay, so exactly how close, as I mentioned, is the subject of more advanced studies, but we can make a few observations if we're thinking about how accurate the approximation is. The accuracy of the tangent line approximation or linear approximation depends on 3 factors. The first factor is the distance between x and a, right? X being the place where you're making your approximation, right? So in this example 2 that we just did, our x would be 1.05 and our a was 1, right? That distance is going to affect your approximation because the further you are away from a, the less accurate your approximation, right? So x closer to a gives a better approximation. That's the first factor. The second factor is going to be the steepness of the graph at A, steepness at A, right? Because if if you remember our square root example that we did, it's a very shallow graph. So if you are at a particular point, right, and you make the tangent line approximation, the tangent line and the graph are eventually going to grow apart, right? But how fast they grow apart is going to be less than if you had a steep graph, like say you're on the x squared graph, then you make a tangent line approximation, and very quickly you can see there's a gap between the tangent line and the actual graph, right? So the steepness steepness of the graph at x equals a, which really means f prime of a, right? So f prime of a smaller is better for the linear approximation. Then the third thing is the concavity, right? So the concavity is going to affect whether you get an overestimate or an underestimate. And that's pretty easy to see. For example, here, if I have the quadratic graph and I'm making a linear approximation at a point, then the line here, right, is going to be under the graph. So if we're thinking of making a linear approximation at a close by point, right? Say I'm over here at x and I think of L of x, I'm on my line at x, versus f of x, right? Where I'm on my graph at x. Then the error in my approximation is really that distance between f of x and L of x. That's something to notice. And the other thing to notice is that if your graph here is curving upwards like a cup, then your linear approximation number is going to be below your f of x, right? So L of x in this case is going to be less than f of x. So our approximation will be an underestimate if the graph is curving up. If the graph is curving down, like we had in example 1, we did a linear approximation for the square root function, right? And we were at 9, and, so a and f of a were 9 and 3, and we did our linear approximation. You can go back and look at the numbers. Let me draw this tangent line a little bit better, right? So this is L of x, and then we went over to 9.2, and we found that L of 9.2, and L of 9.2 came out to be, if I recall correctly, it was like 3.0333 recurring. And if we actually did F of 9.2, which was, the square root of 9.2, that was something like 3 from the calculator, 3.0331, right? So we can see that L of x was an overestimate. L of x was greater than f of x, right? It was an overestimate. And if you think of the curvature there, it's kind of obvious that it would be, right? Because the tangent line is above the curve. If the curve is sloping downwards, or like an umbrella, this curve is kind of curving like an umbrella, the slope is getting less and less, then the tangent line is going to be above the actual curve, and your linear approximation is going to be an overestimate. So we are going to remember that if the graph is concave up at x equals a, that then the linearization or linear approximation is going to produce an overestimate. And we're going to remember that if the graph is concave down at x equals a, then the linearization is going to produce an underestimate. Okay, we have our last problem here. Find the linearization to f of x is equal to 2e to the negative x plus 1 at x equals negative 1, and use it to approximate f of negative 1.2. So it's pretty straightforward with our recipe. We have the point a is equal to negative 1. F of a, put it into the equation, 2e to the negative 1 negative 1 plus 1, right? So this is going to become 2e to the negative 0. Negative 0 is just 0, so this is 2e to the 0, or 2. So we've got a and f of a. Now we need to carefully take our derivative. F prime of a is equal to 2e to the negative x plus 1 times -1 by the chain rule. My inside function is, you can distribute that negative sign and think of your inside function as that. So inside prime is -1, outside function is e to the x, and so out, this is my out prime of in, and this is my in prime. So there's f prime of x, really. And then if I want to do f prime of -1, then I go 2 e to the -1 plus 1 is again going to give me a 0. So 2 e to the -0 times -1 makes -2. This is just like e to the 0, it's equal to 1. So I have my f prime of a is right here, and I have my a and f of a. So I can write my linearization. L of x is equal to f of a, that's 2, minus, in this case, 2, that's f prime of a, times x minus a, right? So be careful. Let's just make sure we are understanding. This is f of a minus 2, or really f prime of a times x minus a. So I'm going to get this equation. This equation here simplifies to 2 minus 2x minus 2. The 2's cancel. So L of x is really just equal to -2x. That's the linear approximation. And I can now take that into part B. So part B is asking me to approximate f of -1.2 using L of -1.2. So that's equal to -2 times -1.2, or positive 2.4. That's our answer to part B. Okay, so that's pretty much it. It's a pretty straightforward lesson. The takeaways really are that if you have a differentiable function, then you can make a linear approximation. So first takeaway is that if f of x is differentiable at x equals a, then it is locally linear. It can be approximated by a line at x equals a. Then it is locally linear at x equals a. And then the linear approximation is L of x is equal to f of a plus f prime of a times the quantity x minus a. That's the equation of the line that you can use to approximate f of x. And then we can, last of all, say that there are various factors that are going to affect the accuracy. And the 3 factors we identified are distance between x and a. We identified steepness, which is really f prime of a, right? The bigger f prime of a is, the worse your approximation is going to be. And then we also identified concavity as a factor. The concavity, we're going to talk a lot about it in the next unit. It means, are you shaped like a cup or an umbrella? And that's going to determine whether your linear approximation is an underestimate or an overestimate. Alrighty, folks. See you soon.